Okay, so who remembers what a force constant is? Got a little setup over here, a little demonstration. Madison, what was a force? What was K?
The only ones in this classroom.
The only ones who count. Madison, what's K in that equation? Can you? Force constant, yeah, but what does it have to do with this little demonstration over here? No. Yeah, what does the K have to do with the spring? You remember? The farther you pull it down, like if I pull it down this far, I have to exert such a force. If I have to pull it down this far, exert such a force, right? The farther I pull it down, the greater the force. So the force is directly or indirectly proportional to the displacement. Directly proportional. And to make a proportionality sign an equal sign, you have to put in a constant. Well, that constant is called the force constant. Okay? So the bigger K is, what influence would that have on your spring? Bigger, huge K. Just imagine a huge K. That would, well, if you take a small displacement, but K is huge, the force would be, it's easier if you write it down probably, right? We said that, right. F is proportional to X. Put in a constant, F equals Kx. Small displacement, huge K, what F then? Just make K bigger and bigger and bigger. What does that mean? You need a bigger and bigger force. That means the spring is really, really strong, right? All right, so it's hard to stretch that thing. They're trying to model chemical bonds after what you see right here, right? We're talking about vibrations, and that's what this is all about. We had angular frequency, okay, and that's what this is kind of review. I mean, we had this in concept previews in the past, so I'm not going to spend a whole lot of time on it. We talked about reduced mass, and I think you even did this once before. You showed that how the reduced mass is, now they call it effective mass, kind of a better word because we're not always, what type of molecule are we talking about if we're going to use this equation, which is the same as that one? What type of molecule are we talking about? There's the D. Diatomic. We're going to get into dipole in a little bit, right? That's going to be important in a little bit, so you remember something that's coming up. But yeah, diatomic. So, but if it's not diatomic, you know, all you do in this symbol, this effective mass symbol, you just have the masses of the atoms that are involved in the vibration. We're not going to mess with that, though. That's way too complicated. So we're just going to stick with diatomic stuff, just like we did in the past. And what they're trying to do is model potential energy and displacement with this plot. Can the right? So the farther you pull it out, right, the more potential energy you have. So just kind of imagine a static picture, right? The farther our displacement, the farther the potential energy is, right? Don't displace it too much. Not very much potential energy. Let it set and not stretch at all. This displacement would be what number? Alice, what number would this displacement be? 0. Yeah, that's its what position? It starts with an E. Equilibrium, right? Okay. So if this is supposed to model that motion, that energy as with displacement. Can the bond ever break, Kathleen? Can the bond ever break? I don't know. Look at the plot. If it breaks, that means the displacement, right? Do parabolas keep on going forever and ever and ever? Right, they do. So this bond can never break. You can always displace it. Does that sound like a good model for a molecule? No, right? They gotta break sooner or later, right? So that ain't gonna work. I mean, it works. You could have little vibrational energy levels in here, and all that sounds great, right? You can do that, but it's gotta break. So something's wrong with it. And that's what this chapter's getting into, this section. Okay, and then if you get into the energies, right, expressed in, here's our energy. And I say that it's expressed in wave numbers because I see what symbol in this equation. Yeah, exactly, I see that guy. So my units of energy are not joules, they're wave numbers. But you can convert it to joules if you wanted, or calories or whatever. Okay, what's that little V? That's the Q, the R with vibrations. We had this, the what number? Quantum number, yeah, right? So V could be 0, if you remember, that's where it starts. So you can get the energy for each vibrational energy level using that equation, but it's according to this plot, so it's not the whole story. This equation is going to get a lot uglier because it's not telling us the whole story. Okay, selection rules. Now you can talk about the D word, dipole. So we're talking about what type of transitions again? Vibrational transitions, right? This bond absorbs the exact right amount of what type of radiation are we talking about? Electromagnetic spectrum? IR. It absorbs the exact right frequency of IR. Does the frequency change of this vibration? And what changes? Only its amplitude. All right? That's a funky thing. You can actually stare at it and count. It doesn't change frequency. It just changes amplitude. Okay. So we have infrared active, infrared inactive vibrations. So some that actually, they're vibrations, but only some absorb IR. The ones that absorb IR are active. What's so special about them? Oscillating dipole, right? Oscillating dipole moment. And then, dang, it'll absorb infrared radiation. Good. What would be an example of a molecule you can spend, I don't care how much money, on an FTIR spectrophotometer, and you're not going to see this molecule? What would be an example of one? Miss Moon? What would be an example of one? Think of something that doesn't have a what? It doesn't have a D-word dipole. Yeah, H2, HH. Just have the same element twice. Any diatomic molecule that's what nuclear? Homonuclear, right? I'm just trying to get into some terminology here, right? So homonuclear diatomic molecules, you're not ever going to see them. That explosive gas, hydrogen, forget it. You're not going to see that on the FTIR. Fundamental transition, it's just the ground state to the first excited state. Okay, that's the fundamental transition, ground to the first excited. Okay, so anharmonicity. Now we can actually start, see how the plot, now there's a limit to it, right? See how you pull the displacement, you pull it out, get that displacement large enough, the bond actually breaks. There's a V max. There's a maximum vibrational energy level. And what's kind of interesting, they call it anharmonic because with this setup, with this spring, I pull it down a little bit, I feel a little bit of force. I pull it down a little bit farther, I feel, more force. They're directly proportional, but it's not the case if it's anharmonic. You pull it, it's not directly proportional. That's why they call it anharmonic. And let's see here. Yeah, so it's not. But notice how it's parabolic down here. So as long as you don't go into very high, IR energies, just talk about the lower excited states, you'll be okay with this kind of stuff. Okay. Our anharmonicity, where'd it go? Our anharmonicity constants, they're not going to be very big. So there's an equation for this. Where did I write this down here? Here it is. Anharmonicity constant. This is in the book. I think you must need it because I wrote it down. Now, what is DE? You have to have really good eyes to see it. You see it? Right? Here's DE. The depth of that potential energy well. The complete depth. But is that the dissociation energy? See how there's a DO and there's a DE? Which one is the dissociation energy? Why is it DO? I would have guessed, you're right Anna's right with DO. I would have guessed DE because DE is the entire depth of the well, right? But it's not, it's DO. Why is it DO? The technical answer starts with a Z. Ooh, good. You should get your little mole for that. The 0 point energy. You can't get to the bottom. It's impossible. Heisenberg uncertainty principle. Okay, so remember, you gotta have to have really good eyes here. But see how V equals 0? That's as low as you can get. Okay, and then the book has some other relationships that I'm going to write down. I don't know if I added these or not. I should take a look at your notes, but there's how D naught and DE are related. Okay. Then there's a couple other equations here for these anharmonic vibrations. Before, where'd it go? There it is. Man, I have all this writing, I can hardly read my writing. Right? Before we had this, to get the energies of our vibrational energy levels. Quantum number, what's the quantum number? V. So there's our quantum number V. So, similar, but okay. This is for the, do you guys have these? Do I have to write this? Do you have these in your notes? For V goes to V plus 1? Okay, I'll write them down then. It's in the book, but you're going to need it for the homework, so it's nice just to have it all in one spot. For V going to V plus 1, how do you get the energy? You use this equation when it's anharmonicity is important. Wave number minus 2, quantum number plus 1, anharmonicity constant, wave number again. And then if you have V going to, what was it? V plus 2, what was that? That was 2 wave number minus 2 V plus 3 anharmonicity constant wave number. Okay, so here's our first. That's regular transitions, but if you're into music, you've heard this kind of terms, overtones, right? So this would be your first overtone. I don't think it really matters. I don't think you need to worry about that. But they're starting to get into that kind of language. Okay. If you're going to use this equation, and you will, let's pretend you're going from V equals 0 to V equals 2. Okay. it'd be pretty clear which one you have to use, right? It would be the top one or the bottom one. It would be the bottom one. But what do you use for V? See the V? Do you use the 0 or do you use the 2? Okay, now follow the notation. It'd be 0 because it's going from 0 to 2. So V to V plus 2. So you have to plug in the 0. You have to plug in the original to follow their convention. Good. Okay. Well, they mentioned overtones. Good deal. We're not going to worry about the Burge plot there. Okay. So vibration rotation spectra. They also call this molecular spectra. So molecules, and just going upstairs and getting an FTIR spectrum. What's kind of interesting, I think, is we think of these plots, right, our vibrational energy levels, right? We're going from one transition to the other. And then we get these, out of that, we get our FTIR spectrum, right? You have wave number down here, and you get some nice little, I'm not very good at drawing FTIR spectrum, but that's the idea, right? If you take this whole thing and just rotate it 90 degrees, you would see all the energy levels. Can you imagine it? You'd see all the different vibrational energy levels. That's what they're trying to illustrate here. They're just taking an FTIR spectrum and rotating it 90 degrees to show that, ooh, now you can see the vibrational energy ladder. Okay? Now, for it to look this nice, it has to be a gas, right? But what they're trying to say is that what you're starting to see here aren't these, it isn't, right? If you see like this line and this, these are not transitions going from there to there. It's all the transitions in between the vibrational energy levels, a gazillion transitions. Those aren't vibrational transitions. What are they? Starts with an R. Much less energy. Rotational. These are rotational energies we're talking about. Rotational transitions. And the only time you're going to see it is if you hopefully get to have an opportunity to do the carbon monoxide lab. Okay? And you'll actually build this thing. And then they have they separate them into 3 branches, a P branch, a Q branch, and an R branch. All it is they kind of tell you here, right, what the change in quantum number is. That's how you get each of those branches. And they tried to show you here in this plot of those transitions, right, how J only changes by 1 or 0 or -1. And all that originates from those transitions. Okay. Okay. There might. And would it make sense if, look at, is this peak more intense than this peak? Did you say yes or no, Kathleen? Is this one more intense than that one? Yeah, definitely. Which one is more populated? Which one has more molecules undergoing that transition? The first one or the second one? If it's more intense, you should have more, right? There's more population to work with. So we've talked about Boltzmann distribution and things, but I kind of like these plots because you don't have to calculate anything. You can just look and see the intensity. Ooh, there's a lot of molecules undergoing that transition. Or there aren't very many populated in that transition. So that kind of gives you an idea here, right? Here you just see energy changes. You don't have any, there's no population info. But there is here. In these spectra there's a whole lot of population info. It's all population info. Okay. For allowed transitions. And then the R branch, I think we need an equation for it. I'm going to dig it up in the reading. So the wave numbers for the R branch, the allowed, quantum number J, U0 plus 2, that's that same B we had from last class period. Rotational constants. That's for the R branch, so that's going for, right, J to J plus 1, or delta J is 1. I guess another way to say that, just write it down. For J goes to J plus 1, right? The same thing. Delta J is 1. Okay. So the homework isn't very straightforward at all, so I wanted to get you started on each of those. Unless you have notes. Do you have notes? You don't. I didn't think so. Okay, so we've got to get you started on this homework. Oh, you need the book too. All right, well, does anyone have a book besides me? Huh? Everyone's gonna have to gather around Adriana and Anna. And I have a book so we can gather around right here too. So we have 3 groups you can work in. Adriana, my book, and Anna's book. Okay, so first question. Number 9. I just like to get them, make sure you have a comfortable way to start, right? And then we'll move on. Okay. So the question reads, 8, 9. An object of mass 1 kilogram suspended from the end of a rubber band has a vibrational frequency of 2 hertz. Find the force constant. Right? Do you see how to get it? You're going to have to mess with these 2 equations to get it. You okay with it? Right? These 2. Which symbol is frequency? Yeah, it's the one without the tilde. There's frequency. Here's force constant. Right? Okay. It's not too bad. And they tell us the mass, so we don't have to worry about calculating a reduced mass, right? Okay. How about the next one? What's the next number? 10. Number 10. Okay. Calculate the percent difference in the fundamental vibration wave number. Okay. And the assumption that force constants are the same. Okay. Calculate the percent difference in the fundamental vibration wave number. Wave number? I did angular frequency. Am I looking at the right question? I am. Okay. What I did for number 10, it's a lot easier when they're typed out. All right. This is how I did it. I calculated the angular frequency because they said that the force constants were the same. I keep looking at the wrong one. But I want fundamental vibration wave number.
Didn't you just use this one? Yeah. And you just
Yeah.
plug in a different reduced mass.
Yeah. I think that sounds good. How do you get reduced mass? Did you hear what? Okay. Adriana was talking about? So the K is the same. How do you get reduced mass? The equation, right?
1 over sodium and then 1 over fluorine.
Yeah. Okay, now the unit, how do you get these numbers? This is, I don't know how many, this is a while back.
Oh, you have to calculate
Yeah, you're starting to remember this. And I wrote that there's a little, you find the table in U units of all these isotopes, right? You find Na23. Then we calculated it. There's a relationship between U and kilograms. And I thought I wrote it. Yeah.
It's in the front.
Oh, here I wrote it down. I knew I wrote it down somewhere. Maybe it's in your front book, but I could never find it, so I scribbled it down. So you got to get it, the U units into kilograms. So that's what I use. And you got to find the table. Oh, that's why I wrote it next to that table. Okay. So find the. What's that? Oh, you did?
Yeah.
Oh, okay. You remember better than I do. Good. Yeah? Okay. I wonder if that's it then. Is there any other tricks to that one? All right. So notice how if you do this, you substitute this into here, those K's are gone because you could factor them out. So really, you don't worry about the K. It's just about the reduced mass. Well, to the 1/2 power, right? And that's all you do. So we're okay with that? Everyone visualize how to do it? That was 10. What's the next one? 11. 11. It is. The wave number of the fundamental. Oh, calculate the force constant again. So if they tell you wave number, exactly. If they it's so messed up in here. If they tell you wave number, exactly, you can get omega. No problem. If you can get omega, you can get over there. Okay? What would be the units of K? Do you remember this? Because you can't just plug in numbers and. Yeah. Here's a hint. Because I usually just plug in all the numbers and I slap on the units at the end. But I don't know. You could really hang on to everything. K has to be F over X. That means it has to be newtons over meters. Newton per meter. Yep. So 11's not so bad. So they're going to start getting uglier here. 21 is next, right? Okay. Maybe not. Maybe not. What was I so worried about? 21. Yeah. The hydrogen halides have the following fundamental vibration wave numbers. My goodness. Life is good, right? Okay. So 21's okay then too. What's the next one? There's just more to do, yeah. 14. Let's pick on someone who hasn't said anything. Kathleen, how would you do 14? Well, you got to be in with a book, remember? He doesn't have a book either. How do you do 14? Let me read it out loud for her.
I gave her the book.
Oh, okay. How would you answer 14? How would you answer that one, Kathleen?
All of them, yes. All of them
It's on that
are
side.
all of them was
14A.
except A, right?
You're looking for a what?
Oscillating wave.
Well, it doesn't. It could.
But those won't show up.
That won't. You want stuff that
Will
yeah,
show up.
that will show up. And there's other stuff besides homonuclear diatomics that won't show up. They just have to have a permanent dipole moment, and they will show up. And you could go through all the work of finding out what point group they're in. That will always work. Or you just look at the molecule and see if he's got a dipole moment. So don't they all have a dipole moment?
Except X. Yeah, but A is
Oh yeah, A is H2, so definitely not H2. I guess CO2, if CO2 is what? It's not going to show up. If CO2 is exactly linear, right? If CO2 is bent, it's going to show up. If CO2 is linear, it won't. How do you find out? You have to do a Lewis-Dot structure. And then you could follow the diagram, Emily, but I don't think you have to. If you see it's bent, you know it's going to be. So I think you just have to draw a Lewis-Dot structure of CO2 and see if it has any what pairs? Lone pairs. If it's got a lone pair up there, it's going to be bent. All right? Okay. Unless it has two lone pairs. Let's see. Where are we here? 22. Okay, 22 I need to give you some information. So this is what 22 reads. If you don't have a book, it reads for oxygen, delta G values. Now again, those are the energies in wave numbers. For the transitions V equals 0 to 1, 0 to 2, and 0 to 3 are, and they give you these three wave numbers. They want you to find the wave number and the anharmonicity constant. Assume YE to be 0. So what you have to do to solve this is you have to make a plot. And these were the little hints that didn't get in your notes. So this is for number 22. I wanted to give you this. I don't know how else you'd figure it out. Given, if you plot delta G versus V, make that plot, you get what's little m and little b? It's linear. Slope and y-intercept, right? So y-intercept is a little b. So little b is 2885.6 wave numbers. And the slope is a negative 104.1. Okay? 2885.6 wave numbers is the y-intercept. So where am I here? Okay. So what we need to do is we need to look at that equation, right? No, that's not what I did. That's not what I did. We're doing, which number are we doing?
22.
I gave you the wrong hint. I gave you the hint for 23. I thought we were on 23. Well, let's just do 23 then. All right, we'll come back to 22. Since I wrote my nice little hint there. So my hint was for 23. Yeah, I must have at some point. We'll find it. Let's find 23. So 23, the first 5 vibrational energy levels of HCl are at these numbers. Calculate the what's the difference between 22 and 23? I don't remember why I did that. Man, you guys need a book to help me out with this stuff. Okay, we're going to do 23. No, these problems, you just got to think about them, and then it'll come to you. 23. The first 5 vibrational energy levels of HCl are these. Calculate the dissociation of molecules, reciprocal centimeters, and electron volts. Okay. So here's where you're supposed to plot these numbers out. Okay. These are the first 5 vibrational energy levels. So you know what all the V's are, you know what all the delta G's are, and you plot it out. So if you plot it out, you get that slope and that y-intercept. Okay. So if that's the case, what's the equation for delta G in the first place? Right? What did you just plot? Well, no, the equation. Delta G V plus 1/2 is... We did this. Let's see.
288,516 minus decimal.
Well, what I'm trying to do is, I'll show you what I'm trying to do. I'll write it all out, then it'll be easier to explain. Okay. So what we did, I'm going to rearrange this. All right. That's going to be minus 2bxe. I'm just going to distribute that. Okay. So do you see how I went, where I just copied this equation and I distributed it to get this one. We plotted delta G V plus 1/2 versus V. So let's just see if you remember this stuff. We did, I don't remember what class we did this in. It was messing with linear relationships and equations. If I plot F versus X, what would be my slope using this equation? What would be my slope? It'd be the K. So in general, the slope is anything you multiply by that variable you're plotting against. Okay? What's my y-intercept if I plot F versus X, and this is my equation?
0.
It'd be 0. So and you could do this a bunch of times, but it's everything that's left over. That's assuming it's in a linear relationship. So we do the same thought process with this. We're plotting delta G versus V. So what would be my slope in symbols? What would it be? Now, when you don't say V, though, because we're plotting, like here, remember we plot F versus X. We said the slope was just everything. We were multiplying times the X. Well, don't forget the negative sign, though. Negative 2 xe wave number. That would be your slope. It's everything you're multiplying by what you're applying against. So slope is negative 2 xe wave number. What will be my y-intercept? Everything that's left over, not just wave number. All right, because we took care of this guy already. It's everything that's left over. So it'd be wave number minus 2x wave number. If there's more stuff, that would also be part of the y-intercept. Okay. Now we know what M and B are. We have 2 equations, 2 unknowns. You can solve for it. Okay. So that's 23. They gave us a whole bunch of stuff. Now in 22, it's probably good that we did 23 first, because you can't do the same thing for 22. Because in 22, where's 22? In 22, they're saying delta G values for 0 to 1 and 0 to 2 and 0 to 3. So you can't plot this out. It's not the same transition the whole time. What you have to do is, all we're going to do is we're going to write out the equation for the 0 to 1 transition, for the 0 to 2 transition, for the 0 to 3 transition, and solve for what they want, right? Calculate, in 22, they say calculate the wave number and XE. Well, how many unknowns do we have? Calculate the wave number and XE. Well, the wave number and XE. So you have 2. So we don't only have to write how many equations. If you have 2 unknowns, you have to write 2 equations. So we'll just write 2 equations. We'll write the equations for the V equals 0 to 1 transition and the V equals 0 to 2 transition. And we can quit there. We don't need to write the equation for the V equals 0 to 3 transition. We don't know what it is anyway, right? Because I didn't write it down. I just gave you the V equals 0 to 1 and the V equals 0 to 2 transitions. Okay? So that's what we're going to do. Where did we write those down? Do you remember where we did that? Here it is. Okay. So there's our 2 equations. We just solve for our 2 unknowns. Now remember, what do you have to plug in for V, though? The 0. In both of them. Because one's going from 0 to 1, the other one's going from 0 to 2. So V is going to be 0 in both of those. Right? And we know what the delta G is. They told us. So we know this. Let's change colors here. We know him. This guy's 0. We know him. So you have 2 equations, 2 unknowns. Okay? So it worked out good that we did 23 first. Okay, 23. So are you comfortable with that one? 23. Where are we now? We're at 8. Okay, 8. Number 8. It says infrared absorption by HBr, and they give the little superscripts so you know what atoms they are, so you know what isotopes they are, gives rise to an R branch from V equals 0. What is the wave number of the line originating from the rotational state with J equals 2? So pretty much just mess with that R branch. I gave you an equation for R branch. Here it is. That's why I only gave you the equation for the R branch wave numbers, because that's the only one that deals with the homework. Okay. And then it said to use information in some table, right? Page 483 is a table. So what's in that table that you could use? Oh, the B number, right? Because look at the equation for the R branch. It's got a B in there. So where are you going to get it? Oh, you get it from the table Anna found on page 483. Okay. Page 483. Number 8. What's the last one? 13. Oh, nice. You should like 13. Which of the following molecules may show a pure rotational microwave absorption spectrum?
Wait, I think we did 13 already. Yeah.
Did we?
Yeah.
Oh, all right. Well, then
Like,
don't have to worry about it.
Which of the following molecules we should
There it
use?
is.
Yeah, we did that.
Yeah. So you're good. So we have 4 minutes to spare if you want to work on this stuff. So we don't have... No, Battle of Flowers is Friday. So...
And that's technically like our last day of school.
Yeah, so that's when our exam is. Our exam in here is Friday morning. Yeah, for chapter 16. Because we're going to finish it. We'll finish it on Monday, and then we'll have. I'm working on them.
The what?
The other exams, and then the instrumental exams are graded. But yeah, the PChem ones aren't. So in here we'll finish chapter 16 on Monday, review Wednesday, exam Friday. Okay, and we have lab on Monday, so don't forget about lab.
So when we turn it in?
Friday.
And we have an exam to study for.
Okay, I'll give you this.
Oh my god, we do? Oh my god, we have Thursday too.
I'll give you this. I'll give you this. But I don't think it's a good idea. I think you should do lab.
Come on.
Okay, what's your other?
The other idea is I want to watch those
Yes, I say yes already.
Watch what?
the rest of all those string theory
I
movies.
wanted to see the rest of that too.
But it's you got probably 2.5 hours to sit
You do
in
it
here.
in lab.
Yeah, we have to do it during lab.
That's what I'm saying. That's your choice.
Yeah,
I could do that. I could actually do that.
we actually bring
I like
popcorn
those.
this
Those are
time.
very interesting.
Popcorn.
So 2.5 hours, you guys are willing to sit here.
Yeah.
With
Yeah.
food.
Why not?
And
I mean, we
drinks.
sit
We'll
for
bring
another
snacks.
regular movie almost that long.
Yeah.
Yeah.
All right. So that
As long as I eat before we get to
does. Is everyone okay with that?
Yes.
Well, PChem labs are so good for you.
Ask Rob.
We're gonna learn something out of that too. I'm pretty sure you're gonna have a paper for us.
Yeah, I have to have a questionnaire or something. Yeah. All right. We'll do that then. So Monday, what time does lab start? 2:30. 2:30. God. All right. Well, we're here that long anyway.
Exactly.
All right. So we'll do that. Fine. So the questionnaire has to be turned in right away so I can get it back to you.
So pretty much at the end of the video.
Yeah.